You hear me, right? Right. So we are talking about AES. So today we finish AES and we start the modes of operation. So AES, we have seen almost all the feature of AES. So just to recap, it is a block cipher. It is 10 round block cipher. So this is the picture of this block cipher. So we have this is a 10 round AES. So we have some plain text. Plain text is 128-bit, and also we have these are the operations we will perform: add round key, sub byte. Actually, this is sub byte, shift row, mix column, add round key. And in the first round, we have extra add round key. And this the first round key is nothing but our original key shared between Alice and Bob. So without any risk, we are just XORing. We are just doing this operation. And then we do this for 10 rounds. So up to 9th round, we perform all these 4 operations: sub byte, shift row, mix column, add round key. And in the last round, we have one operation is missing, mix column. And this round key, so we need 11 round keys, and each round key is 128-bit. And this round keys we are getting from the secret key shared between Alice and Bob, which is also 128. And we have seen in the last class how we'll get these round keys. And basically the first round key is the original key between shared in with Alice and Bob. So this is our, and then the final output is our ciphertext. So this is our block cipher Rindle AES. So this is the encryption. And while decrypting, we have to do the reverse. So we have to add round key same as reverse of add round key, because it is just XOR, bitwise XOR. If we just bitwise XOR, it will give us the same. And we know the reverse shift row, because shift row is just shifting the position. We'll do this reverse shift. And sub byte we can just we had taken the affine transformation, if you remember, in the last class. So that will give us the inverse test box. So we have to perform the inverse test box on each of these state or each of the byte, and we'll get back the this thing inverse test box. And the mix column also, inverse mix column, we know that this is this also can be written in the matrix form, and then we can apply the inverse operation on that. So that is the decryption. Okay. So so let me show you the one. Yeah. So this we have already covered. This we have discussed. This as a mathematical foundation for having this S box. We do have a proper algorithm for finding the S box. So that is the good thing. Instead of DSS box, here we do have a proper algorithm for finding that, and we have a proper mathematical formulation to get that S box. We use the finite field here. So yeah, so this thing we have covered, and yeah, so this is I think one part was left in the last class. This for key generation, key scheduling algorithm. This is our key scheduling algorithm for AES. We have a 128-bit secret key shared between Alice and Bob, and from there we need to get the round keys. Round keys are also 128. So this secret key we make it into the state again, because the AES all the AES operation we are doing in a state. We are storing in a matrix, 4x4 matrix, and each entry is a byte. So then it will be 128, total is 128-bit. So that key which is shared between Alice and Bob, we are dividing into the byte. So K0, K1, K2 like this, and then we store into the matrix. And these are our words: W0, W2, W3, W0s are the words. Words means 32-bit. 4 byte can together be a word. So this W0 will be initialized by this first 32 bit of the secret key shared between Alice and Bob, and this W1 is the next 32 bit of the secret key, W2, W3, and that is our K1 basically, I mean the first round key. And then how to get the second round key? That is by using this formula, this functions, this connections. How is this happening? So we have a G function. G we have to discuss. So G function can take the 32-bit input and which can give the 32-bit output. We take W3 and we apply G function on that and we get 32-bit output. And this 32-bit we XOR with the W0 and then that will be our W4. And so once we have a W4, then we take W4 XOR with this W1 and we get W5. Once we have the value of W5, we take that value and we XOR with W2 and we get W6. Once we get W6, we XOR with W3, we get W7. So this is our, again, 128 bit. This is our next round key. And this value we copied here instead of W0 to W3, and then we perform the same operations to get the next Ws. Okay. The next Ws. 1 minute. Connection problem. Sorry, the connection was lost actually. I made a Wi-Fi again. Can you hear me now?
Yes, sir.
Hello?
Yes,
Yeah.
sir.
Yes, sir.
Thank you. So, yeah, so this is the, is this clear? This W's? Now we need to know what is G. Any question? So G is taking 32 bit G is having some operation like rotation operation. Again, we use the sub byte, AES sub byte on this each of these 8 bits, and then we use some constant addition, XORing basically. So these three operations will perform in G function. So so G takes this B0, B1, B2, B3. So they are all, G is 32 bits, so they are all 8 bits. So 1 byte each. So then rotation operation, rote word. Rote word means this B0 will circular shift. So B1 will come here, B2 will come here like this. So this is the rotation operation. Rotation word, because we are rotating 32 bit. Okay, but these are all bytes. And on each of these byte, then after that, after this rotation, we'll perform the S box. So that is calling, but we'll use the same S box of AES. So that will perform. So we have the 8 bit after this rotation. So on this each 8 bit, we will perform the S box. S box will take 8 bit to 8 bit. So again, it will be 32 bit. And on this 32 bit, we'll add some, we'll extract some constant. So these constants are given in the in this. Where is the table? These are the constant. This constant again 32 bit. So these are in hexadecimal form. If you see, this constant is 1B00. So all are 4 bits. So there are 8 4 bits. So that is 32 bit. So these we are just XORing with that. So there are how many constant we need? We need 11 constant, because sorry, 10 constant, because for the first round key we are not doing this business, because first round key is the original key. We just copied in W's. We are just taking that, and we are XORing straight away. We are XORing with the plain text. Okay. So the first round key is the secret key shared between Alice and Bob, and from the next round onwards, we will do these things. So any question? This is the G. Now, if we look at one single round of AES, that looks like this, and that's from this picture you can see, that's why it is become secure. So let me just bigger. So this is our plain text, or we are storing in a state. So this is a state is we are applying the S box. So we take each of these bytes and we apply S box. It will giving us the new values. And then we are doing the shift row. Shift row means we are changing the position of this. Okay, we are changing the position of this. Changing the position of this. Can you hear me? It is a shuffling
Yes,
the byte position. Yes,
sir.
shuffling the byte positions. So that is the shift row. So you can see. So there are so many things we are doing in a single round of AES. So we are just shifting the positions, and we are just uh, so some mixture is there. Then finally we are going to add the round keys. Anyway, so then after that this is the shift row. After that we are taking the this column, first column, and we apply that operations, column operation, mix column operation. Then it will give us a new column, new values. So that also we are doing, and then finally we are doing the add round key with this. Okay. So is this okay? So this is our one round AES, and that makes AES to be secure. So far there is no attacks on full round. AES is still the standard. I mean Rindel. Rindel is still the advanced encryption standard. So there is no attack which can break full Rindel. So that is the beauty. Okay, any question? So let us take an assignment here before we move further. So is the whiteboard is coming?
Yes, sir.
So this assignment you need to submit. I'll send you the this thing. I'll send you the implement a new block cipher. Why new? I'll discuss. So I want you to implement basically the AES. So you first do the AES. So this has few steps. First you implement AES, both the encryption and decryption. My board is visible to you, right? I am writing over here.
Yes, sir.
Thank you. So this is the first thing you have to do in everything in C code. So no other language I can understand. Okay, so after that, once we have it, so I want you to have a indigenous block cipher. So like you have AES is 10 round. So what you can do, you can break it into 5 round, 5 round of AES. And in the middle, I want to introduce you some Fistel cipher. Fistel, I mean, how many rounds? Maybe 4 round or 6 round, or maybe 4 or 6 round. You have an option there. Your computer, your program should ask for this option. How many rounds you want to introduce? 4 round or 6 round. Then after that, you have a followed by a 5 round, another remaining 5 round of AES. Okay, so so in that here also you can you need to have the round keys. So but Fistel is the our Fistel is 64-bit, but you have to somehow extend that. I mean, I want you to leave to you to get this design, and in your write-up the design also should be there. What type of I mean, how we are extending the Fistel for one, because this is 128-bit. This is the plain text. You apply the 5 round AES, you will get 128-bit. Then you apply 4 round of Fistel structure. So there you have to be a little careful about how you manage this those DSS box. You can get the AES box if you like, or something. I mean, I wanted to do something new. And then finally, after that 4 or 6 round, whatever your computer, I mean the output will be 4 round or 6 round. Then after that, you will have another 5 remaining 5 round of AES, last 5 round, and then that will give you a ciphertext. Is this clear? The assignment?
Yes, sir.
Sir, I have a question.
Yeah, please.
Sir, what will the key scheduling algo for the Fistel cipher be same as that of the AES?
No, that's why I want you to think about that. Key scheduling algo for if we use AES, then you have to extend that key scheduling algorithm because it should not repeat, na. So that's why I want to have the design from your side. I just
Okay,
want to introduce some new, not new, because this everything is we are using old things, because see, this AES is secure. So if you have to design a new block cipher, so instead of design from the crash, we can take a underline secure block cipher, then we can do that. That is the technique we have used. Okay. So when we'll put the deadline, and this is serious deadline, and I'll send you one email ID I created. Last time I thought this is classical crypto, so not to submit, but this you have to submit, and this will carry some marks also. So today is 15th. What about 20th? Is early or?
No, sir, we already loaded with so much of assignment in this
Okay, so you suggest a date then?
The 30th.
the
30th.
30th.
30th September.
So this is a firm deadline. Okay, no more extension.
So what is the marks that is carrying?
No, you see, this is a continuous assessment. So you submit it. I mean, marks, we cannot tell that this is one class test mark, something like that. But Since it is continuous assessment, also your attendance is there. We are taking from this MS team, but we have no way to understand whether you are attending or you are just online. So those things are there. So this is a assignment, implementation assignment, and it carries some marks, as I said. But how much marks that we can decide.
And so last week you said about some tests. So when it
Yeah,
is going to
test.
be held?
Yeah, actually I forgot to send the mail. So this week let it be. We already make the question, but we'll take next week. The syllabus will be remain same up to the
So
modes of
the same
operation.
means like from the very beginning to up till now.
No. I'll tell you. I mean,
Okay,
maybe
sir.
LFSR based stream cipher and AES, and then the modes of operation, which will start today. Okay.
Okay, sir. So next week, sir.
Please
Yeah.
send a
Next.
mail
Next.
regarding.
Next. I'll send a
Yes,
mail regarding
sir.
this also, regarding the assignment also.
Okay,
Yes,
sir.
sir.
Okay.
Thank
So
you.
any doubt about this assignment?
Sir,
I'll
we can only implement in C or any other language.
C. No. I can only understand C language. That is my problem.
Okay, sir. Okay, sir.
Okay. So we can just pause it. Now we'll start new the modes of operations. So I hope AES is almost okay with us. Okay, modes of operation. Modes. Okay, modes of operation is suppose we have a block cipher, anything, it could be DES, AES. We have a given Alice and Bob. They are having a key, secret key, and they have a block cipher for encryption. And this is some fixed block cipher. We know some fixed bit, L bit, say 100 bit. We have a 100-bit block cipher. So far we haven't seen 100-bit. We have seen 64-bit. But anyway, for the, and this is the key. Key also has some size. They have this black box. Okay. Both of them. Everybody is having this. Now, other than Alice and Bob also, they knows everything about this. Only thing they, other than Alice and Bob, they are not having the key. Okay. So now, suppose, but the message Alice wants to send to Bob, that may not be 100-bit. That is the problem. I mean, that may be more than 100-bit. That may be say size of this is say 1000 bits. Then the question is how we do this. How we do this encryption on this message using this black box what we have. So the obvious way is to do this. Suppose we have a message of say 100 bits, 1000 bits. We break it because we have a block of size 100. So we break it into 100. Dot. So this is the first block, second block, third block, like this. So we have 100. So this is how many blocks? 10 blocks here. And what we do, we have this black box, block cipher. We have the same key, and we get Y1. This is block cipher encryption. And we have another block. We encrypt using the same key. This is important, same key, because this is block cipher. In the stream cipher, this is a difference, fundamental difference between block cipher and stream cipher. In the stream cipher, we'll perform similar operations, but there we'll use the different keys. Those are called key stream, right? But in block cipher, when we do this encryption business, we'll use the same key, and we'll get these blocks. Dot. Our good friend. We have E, and we get Y10. Anyway, it doesn't matter how many. What is the length, and this may not be of this. If the last block is not 100 bits, so we can have some dummy bit over here, additions. So this is what is called encryption, and this we send. This is what Alice is doing, and this way Alice will send to Bob. These Y's, Y1, Y2, these blocks, Y10. So Bob will receive these Y's. So then how Bob will get access? Again, Bob will apply the decryption. Alice use encryption, Bob will apply decryption using same key, get the x1. Y2, Bob will apply decryption using the same key, get the x2, like this. Get the x3, x10. This is quite obvious way one can think for doing this. What is called encryption for more than which is size is more. So this is called electronics code board mode, ECB. ECB. This mode is called ECB. ECB modes of operation. ECB mode of operation. We are doing this thing. Any question on this? So if the last bit is not of length L is the size of the block separator, then you have to append some dummy bit over here, and then the Bob has to know that how many bit is the exact plain text size. Then Bob can, after decryption, Bob can do the discard those dummy bits and then get the message back. Okay, but this modes has having a serious problem when we do the when we encrypt like what is called image. Say image, we are encrypting an image. So can you tell how to encrypt an image? Any idea? How to encrypt an image? Suppose we have an image, say my picture. We have an image. How to encrypt this? We have an image. Alice wants.
Sir, a image can be represented as a matrix.
Yes,
So
how?
we can, sir.
Yeah. So yeah, that is
And a
correct.
matrix.
Image can be represented as a matrix because image is a. I mean that is the digitization we do, right? So, but how? That is my question. So anyway, this will run in image processing. So what we do usually, we divide this into some blocks. And for each blocks we pick a value, and that is called pixel value. Pixel. So depending on our resolution, how much we want, we have the size of this block. So image will, so these are the pixels. So basically this pixel will represent this box, this continuous box. So that is the image digitization, because we cannot handle with this continuous business. We have to somehow digitize this image. Digitization means we will take the matrix and then we will do every image processing. If you go for image processing course, you will see we will perform many operations over there. Image segmentation, image, so those things are on this matrix. So this will basically convert into a matrix. So that matrix is basically this pixel value. So P1, P2, something like that. So these pixel values. So once we have this matrix, then we can think for doing the encryption. We can think for doing the encryption like we convert this into again the binary. These are the values, so we can convert into binaries, and then we have a big binary. Then we have binary matrix like this. Then we take this 64-bit if we are using a DES 64-bit like this. So then we apply this, or you can think this as a vector also. So matrix can be think as a vector, right? Big vector of. So then these are all 0, 1 bits. So we break it into these L bits. Then we perform these operations like encryption, and we get the outcome. We get the outcome image. Again, we convert this into pixel values. I mean, we get back the pixel values, and we again try to print this JPEG image or something like that. But if we do that, we have a problem. What is that problem? I have to show you some website. This is Wikipedia website. I just share you this. Let me share you one. So this is the this is, if you Google it, Wikipedia modes of operation, you get this page. Okay. So suppose this is the image we want to encrypt. Alice wants to send this message to Bob. This is the message, penguin. So they are asking, suppose they have a logo competition, so they want to have a logo in their some cigarette vision. So sorry. So they have decided to use this logo of penguin. But Oscar does not know which logo they have chosen. So what Alice will do? Alice will digitize this. Alice will convert into pixel values and then get the matrix and then encrypt using the ECB. Then it will be looks like this. Is visible? Can you see the outcome image? I mean the.
Yes, sir.
Yeah. So this is the. Is this secure? I mean, by seeing this, you can see, we can easily see this is not Saurabh, this is penguin, right? So that is not secure. But why this is coming like this? Any idea?
Since the key is same, so the pixels having the same color will be decrypted to the same thing.
Yes, exactly. So since its pixels are, if our plain text is same and the key is same, so if the plain text is same, it will map to the same ciphertext. So then the edge will be visible. So here, if we take this, if we take this here, this plain text, and it will, oh sorry, here original. If you take this plain text, it will convert into same. So that edge will be clearly visible, because as you said, if say we are using the same key, if the pixel is, if the plain text is having the same value, then it will give us the same ciphertext, because we are not getting, we are not having any feedback kind of thing. So to destroy that, we use different techniques of doing this encryption. So that is what is called operation. Any question? So we have to, yeah. So this is not secure. So ECB is not secure because of that thing. So we will discuss some other modes of operations, say CBC. So these are all given in the lecture note. So I'm just so CBC in cipher block changing modes of operations. Okay. Let me just write the picture of this. So what we do in the CBC modes of operations, so it is also encrypting a block of messages. So here also we have this x1, x2, x3, and so on. Say xk, say. Anyway, k we use for key. So xl we use something purpose. So xm, yes, xm. Anyway, doesn't matter the index. So now we'll what we do, we have x1, we just XOR with this with some IV, initialization vector. Why first one has to be some IV? Because first one we have no feedback, you need to sync. Sometimes this mouse is not a good friend. Yeah, I get back. Yes, last time I couldn't. Anyway, so what we do, we XOR with this, then we apply the encryption, either AES or DS, depending on which is our favorite block cycle, with the same key. And this is our Y1. Okay, so this Y1, we take it into the feedback for the next X2. When we do the X2, we take this Y1 XOR with this because first in the first round, first case we don't have anything. That's why you have to take help of some constant, like some IV. This is insulation vector. So again, this is the same key, y2, and you do this with x3. This is b twice XORing. So this is same value, same size. So you can easily do this business. This is y3, and then we have a good friend dot 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 dot. Good. So this is the encryption. This is CBC, modes of operation encryption. This is encryption what Alice is doing. What Alice is doing. Then after this encryption, Alice is getting this ciphertext blocks y1, y2 dot dot dot. I think ym we have seen. That is the output of this. And then Alice will send this to Bob. What is the decryption then? So Bob is receiving this y's. Bob has to get back this x. How Bob will get back? Any idea? From y1 say. From y1 how Bob will get back this x1? Anyone? Come on. Any suggestion? Are you there?
So first use the decryption and then solve with the initial vector.
Yeah, that is the x1. And then the next one, how to get from y2, how to get x2? He has to get x1, x2, all the plain text blocks. So from y2, how will get x2? Same.
So first decrypt and XOR with y1.
XOR with y1. That's all. So just the reverse of this. So that we will do now. So this is the decryption which Bob will do. So Bob is having y1. So Bob will first decrypt it using the same key, get something over here, and that Bob will XOR with IV will get x1. And then y2, Bob will decrypt it using the same key and get this. This will XOR with y1 and get the x2. And y3 using the same key, decryption. Get this with this y2 with this x3. And then we have a friend dot 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 dot. This is okay now. So this is Bob is doing. So the beauty is, since we are taking the feedback, so this will give us the image. If we apply this mode of operation on this image, the result will be fantastic. So let me just share this. Here is the yes. So it will be this one. So that penguin will be this one. So from here you cannot say this is penguin or Saurabh. So it is secure, no? So that's it. That's why if we use the image type of plain text, then we use that to destroy that uniqueness. We have to use the feedback kind of things. Okay, so this is what is called. Yeah, this is this picture they got applying the AES. So AES modes of operation. So underlying block cipher is AES. So this was the plain text, and we got this was the plain text, and we got this is so we got this is not secure. This is ECB, and we have CBC modes of operation. That is secure. Okay. Okay. So then we talk about another modes of operation, like another is cyber feedback modes, so CFB. So instead of doing the XOR first, we can just do the encrypt and then we can do the XOR. I mean, even we can do the encrypt on the IV. So that is called CFB. So let me just cyber feedback mode. Are you seeing the board now or what? No. Yeah, now board is visible, right?
Yes, sir.
Thank you. So CFB, cyber feedback mode. So this is another mode of operation. So here we have we first use the encryption on the IV. So we have this plain text block x1 x like this. We have to get the ciphertext block. How will do that? So we first encrypt it. We encrypt the IV straight away, and then we XOR with this x1, and then we get a y1 over here. And then what is the next one? What is the next one? So we just encrypt this y1 again using the same key, and then we XOR with x2. This is our y2, and then again we will encrypt using same key. We get this will XOR with x3. We get y3. Then our good friend. Dot, 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 dot. This is the encryption. Then the question is how we'll decrypt it. So this is Alice is doing. So Alice is getting this y1, y2, y3, and then Alice is generating this and send it to Bob. So now suggest me how Bob will decrypt it. Any idea?
Decrypt the
How
IV
Bob will
and
decrypt
XOR
it?
with the Y1.
Yeah. So decrypt the IV. We need to decrypt it. Bob is having this y's. Bob has to get back x. Say x1. How Bob will get back x1? Any other solution?
Encrypt, sir, encrypt.
Yeah. So Bob knows y1. Somehow Bob has to get this values. If Bob get these values, then Bob can XOR with this y1 and get the x1, right? So to get these values, Bob is having IV. Sorry. Bob is having IV, so Bob can again encrypt. So that is the beauty. We don't need to decrypt. We can encrypt because DES. Anyway, some block cipher maybe we don't like to decrypt again. So here we are doing the encryption again. So we just encrypt the IV. We get the value over here, and then that value we XOR with this y1 and we get x1. Similarly, we have y1, Bob is having y1. Bob again apply the encryption using the same key. So Bob will be here. Bob will get the value over here, and then Bob has y2. So Bob will XOR it's cancelling out. So Bob will XOR with this value and this. It will give us the x2. So like this. So let us just get the picture. So Bob will do the same thing, IV encryption using the same key, and this Bob will XOR with Y1 and get the X1. And for Y2, so Bob has Y1, Bob will encrypt this Y1 using the same key, and Bob will decrypt it using, Bob will apply. Anyway, so this is another modes of operation. Can you think one more modes of operation over here instead of say we can first encrypt then this thing. Even there are counter modes of operations also there. So those are given in the extension book, or you can get it from the lecture slide. Any question before we stop? So this is the modes of operations. So this is the way we encrypt the bulk message using the block cipher or stream cipher. So so this is what is for the AES and modes of operations. So maybe from tomorrow we'll start some mathematical background on it, because that is very much essential for our public key crypto system. So before we start the public key crypto system, we should have that background. So I'm thinking to start this mathematical background from tomorrow. Okay. So any question before we start? So we had two announcements. One is in this assignment, implementation assignment. I'll send you the mail where to submit, and the deadline is the 30th. And then we have exam on the next week, next Thursday, and the syllabus will be this LFA server stream cipher and AES and this modes of operations. Okay. So let me stop the recording.